Whenever it's ready. Are we on air already? Okay. Okay. Thank you very much, everyone, for attending. I'm more than happy to introduce our speakers for today, who is Jorge Otero. He's a very good friend of the Institute and of our group, because he was doing his previous postdoc with us here at the IAEA in Granada. After the PhD that he did at Instituto de Astrofísica de Canarias, IAC, here in Spain, and now he's on his second postdoc at the Istituto Nazionale di Fisica Nucleare in the section of Padova in Italy. Besides his youth, actually, Jorge has a very good CV. He's a very productive young early career researcher. He has more than 100 publications, of which more than 10 of them are either first author or publications on which he has a major leading role. And he's specialized on AGN, mainly blazar research from the spectral range perspective, with lots of emphasis on very high energy gamma ray observations and optical observations, mainly polarimetry. He has also a profile for multi-spectral range polarimetry, which he has dedicated some part of his years to his research to the last years, mainly on getting involved each time more on X-ray polarimetric observations of blazars. He's going to talk about actually the first results on extragalactic science from LST-1, which is the first telescope of the LST collaboration, which are the prototypes actually of the CTAO observatory, which is being built in Padova, also in the southern hemisphere in Chile. And just to finish, just saying that he's today here as the coordinator of the extragalactic group of the LST collaboration, on which he's serving since a couple of years, actually since he was a postdoc here. And the floor is yours. Perfect. Go ahead.
Thanks, Ivan, for the introduction, and also for inviting me this week after the last week's meeting. And continue with this intensive, very high energy week that we had, also with Giacomo's seminar on Tuesday last week from Paul Border, from our physics coordinator in the collaboration. Today I'm gonna talk a little bit about the early science that we have been doing with LST-1, and as Ivan already advanced in the introduction, focused on my expertise, so extragalactic physics with LST-1 at very high energies, and also of course with synergies with different instruments. And to motivate a little bit the why studying extragalactic sources and AGNs and blazars in particular, I want to start showing this image that probably it looks already familiar to most of you. That is the gamma ray sky as seen by the Fermi-LAT satellite. I think this is after 15 years of observations. So already from looking at this sky map, we see that besides the very populated galactic plane, we have extragalactic sky dominated by point-like sources. And the thing about these sources is that more than 60% of them are AGNs, and most of them are AGNs, and more than 60% of these AGNs are blazars. So we are already start seeing why blazars are important for us in the gamma ray regime. And AGNs and blazars are simply active galactic nuclei, so in the central regions of galaxies in which we find a supermassive black hole that is accreting matter, is surrounded by this set of regions of structures, so the accretion disk, the dusty torus, Broadland region, etc. And some of these are able to develop to launch these highly collimated relativistic jets, what we call the radial out AGNs. And blazars are simply the case in which this jet is pointing towards us. So we see their emission boosted by relativistic effects, so they become one of the brightest sources in the universe. Their emission is basically characterized by this spectral energy distribution with this double hump shape, in which the low energy emission, depending on the blazar type, from radio to optical, UV, X-rays in the most extreme cases, is produced by synchrotron radiation of relativistic electrons moving in the jet under the influence of a highly ordered magnetic field, and the high energy emission is still under but it is basically interpreted either with leptonic or hadronic scenarios. And there's a lot of physics that we can do with AGNs, and specifically at high energies. They are, of course, one of the candidates to emit extragalactic cosmic rays. So one can do cosmic ray studies with AGNs. We can also study formation, collimation of relativistic jets. Of course, we can study the structure and the particle acceleration mechanisms within these with jets, and they have even been associated with extragalactic neutrino emission. They actually are one of the most solid candidates for extragalactic neutrino emission, but their interest goes even beyond these topics, as they can also be used for proving some more exotic physics topics, such as action-like particles, dark matter, etc. And as I said, in the gamma ray regime, the Fermi-LAT satellite has been monitoring the sky for 17 years with an amazing scientific production. But what about the highest energies? So in the GeV-TeV regime. In this case, we are limited by the size of the instruments that we can launch to space, and the fluxes at these energies are already very low. So we need really very, very big collection areas to study these regimes. And for this, we have developed the image atmospheric Cherenkov telescope technique that we have been using in the last few decades with telescopes such as MAGIC. That is the one that I'm showing here in this picture. And this technique works in the following way. We have our source of gamma ray radiation, in this case an extragalactic source, a blazar, an AGN, and we get a gamma ray that is coming towards us. And whenever this gamma ray reaches the atmosphere, it interacts with particles in the atmosphere, and it creates these cascades of secondary photons and particles that develops in these what we call electromagnetic showers or electromagnetic cascades. And these secondary particles travel through the atmosphere at a velocity higher than the speed of light, and this produces this very faint bluish UV Cherenkov light, and this is actually what our telescopes detect, as you can see in this small video here. And once this Cherenkov light reaches our detectors, our telescopes, as you can see here, we basically take an image of this Cherenkov flash, of this shower, that we later can parameterize. We can study the size of this image, its characteristics, to reconstruct the information of the incoming gamma ray. We see these elliptical images that we can parameterize with what we call the HELAS parameters to understand what were the characteristics of the initial gamma ray. Basically, its direction, energy, so we can trace them back to the emitting source, basically. And this is what we've been doing in the last couple of decades with the current generation of telescopes. So MAGIC here in Spain, in La Palma, HESS in Namibia, and VERITAS in the US. And with very high success, you can see here how the number of discovered sources at very high energies has been increasing, especially since the start of operations of this new generation of Cherenkov telescopes. And of course, we are now, after more than 20 years of observation, reaching this kind of plateau, because we are already starting to get limited by the sensitivity of our telescopes. And this is what we have reached so far. So again, we see this is an image of the very high energy gamma ray sky. And again, we see a very populated galactic plane, as we saw for lower energies with Fermi-LAT, and same as before, a lot of extragalactic sources, point-like sources, and most of them, in this case, even more than 90% of them are blazars. So again, even in the very high energy gamma ray regime, blazars are one of the most important sources for extragalactic physics. And this is, as I said, with the current generation, but now we are moving towards the future observatory. This is the Cherenkov Telescope Array Observatory, CTAO. You can see here a very nice representation of how the observatory will look like in both sides. In the north, again in La Palma, in the south in Chile. That is currently under construction, and it will bring a sensitivity 10 times better, as you can see here, with respect the sensitivity of CTAO after 50 hours of observation with respect to that of MAGIC, HESS and VERITAS, so 10 times better sensitivity than the previous generation. And it will also cover a wider energy range. So besides allowing us to go for fainter sources and more precise studies, it will also allow us to study our very high energy gamma ray sources at lower and higher energies. This is a layout of how the observatory, how the telescopes will be distributed in the northern array. And this is a photo that I actually took 2 months ago exactly from La Palma. So you can see already the very very highly advanced state of the different LSTs of the northern array. So LSTs 2, 3, and 4 that are being built and finished basically as we speak, and the LST-1 that is already in operation. So this LST-1 large size telescope prototype is the first telescope of the northern array. It's been in commissioning and operating since 2020. So it has been already taking a lot of science data that we have been using for the first science of the collaboration. And one of the most important characteristics, at least for extragalactic science, is that the LSTs are optimized to observe the lower end of the very high energy regime. So it has a lower energy threshold than the current generation of Cherenkov telescopes. So we can go down to around 30 GeVs in energy. And this is especially important for extragalactic science because in our case, we are basically limited by the attenuation from the extragalactic background light. So basically, this is a collection of infrared optical photons from the star formation history of the universe. And the thing about the EBL is that it can interact with extragalactic gamma ray photons on the way to Earth, creating these electron-positron pairs and attenuating the intrinsic gamma ray emission that extragalactic sources emit. So we observe lower fluxes than the ones that these sources emit in reality. And this attenuation is more important with energy, so higher energies get more attenuated than lower energies, and also with distance, because the longer the distance that a photon needs to travel to reach Earth, of course, the higher the probability is to at some point interact with one EBL photon. And this has been basically the main showstopper for us for detecting more extragalactic sources. And thanks to the lower energy range of the LSTs, and also in the future the better sensitivity of the CTAO, this is actually one of the main goals of the LSTs in particular, and the CTAO as an observatory. So push the boundaries of the known very high energy gamma ray universe farther than Redshift 1, that is basically the limit that we have been able to measure so far. And with this, I'll start showing a few first extragalactic results with LST-1. Extragalactic science has been one of the main goals of the first observations of LST. We have accumulated already more than 1,000 hours in the past few years, observing several AGNs and blazars, and monitoring some of them quite regularly. Most of them are already known from the previous generations. I'll be coming back to this almost in a while. But this, of course, is a very, very good result to prove that our instrument is working, is doing good science, and there's still a lot that we can learn from sources that we have already detected before. So I'll start showing just some very brief results from the first extragalactic publication of the collaboration that has basically, as a proof of concept, published some of the first interesting results on a few already known blazars, starting from the very well-known Markarians, so Markarian 421 and 501, that are some of the brightest sources in the extragalactic sky, but they are also very, very close, and they are visible almost during almost all the year. So they are very good targets for monitoring in our case. So we have between 2020 and 2022, we have invested more than 30 hours on these sources, and we have been able to catch very interesting flares actually from them, like the one that I'm showing here that even present the very fast minute scale variability. And yeah, again, I'll be talking about this kind of very fast variability events in a while, but they are actually very rare and very rich in the sense of the physics that we can extract from this fast variability at gamma ray energies. Markarian 501, same. We have observed it for roughly 40 hours in this first couple of years of operations, showing actually a very noticeable variability, not also in its emission, but also spectral variations that we cannot often characterize with such precision at very high energies. And this actually holds a lot of information regarding the particles that are responsible for this emission. With this, we can trace back changes in flux to changes in the particle population that is responsible for this gamma ray emission. So the Markarians are two of the closest sources to us, but we have also managed to detect sources that are relatively far away from us, understanding from far, as I said, in the standards of very high energy observations, because of the EBL attenuation. These are, for example, these 1ES 0647 and PG 1553 that have been very well characterized after just a few hours of observation, when with the previous generation of telescopes for such good characterization, we typically needed even brighter flares or more iterations because of the higher energy threshold. And actually, this is an interesting study that this paper has presented, that through some simulations of the performance of the instrument and different characteristics of blazar flares, they have been evaluating the detectability of sources with LST-1 farther than this Redshift 1 frontier. And we see that actually LST is well suited for breaking this frontier in the near future, if the conditions are optimal. And yeah, as I said, all this set of results has been already published in the first Extragalactic Science publication of the LST collaboration. You can check this in more detail here. And yeah, I'll be also giving some couple of hints of another important monitoring campaign that has been historically running first at the MAGIC telescopes and now also in LST, that is the observation of radio galaxies at very high energies. These sources have actually a lot of advantages because they are the jet is not pointed towards us, so we know very well their distances because of the host galaxy very invisible, and they typically have very rich and populated acidity. So we can do very good multi-wavelength studies complementing our very high energy data with data in basically along all the electromagnetic spectrum. Thanks to the observations that we can do of the radio jets, we can also know very well the Doppler factors, the acceleration mechanisms, etc. And they have shown in the past very powerful flares. Since this jet is not pointed towards us, the triggers sometimes are a bit challenging, but there's a lot of physics that we can do with radio galaxy observations. And two of the most observed are these NGC 1275 and IC 310 that belong to the Perseus cluster. And yeah, I don't want to go into much detail in this campaign because this was actually a seminar by our colleague Mireia Nievas from IC. So everyone that is interested in radio galaxies I encourage you to go to the IAA's seminar YouTube channel and check this seminar out. And now regarding observations of variable blazars and AGNs, I'll be commenting some of the most striking results that we have been obtaining through the Target of Opportunity program. That is basically one of the most important programs in extragalactic science. This is because first, blazars are highly variable, and second, because so far most of them, we have only managed to detect them through these flaring states. So we rely a lot on these Target of Opportunity programs to increase our sample of known very high energy blazars. For this, we of course rely on external alerts from different facilities. We often use Fermi-LAT as our input with a couple of automatic analysis pipelines that we regularly check to trigger these observations, but we have also set up different tools like this optical flux monitoring through the Swiggy transient facility that, again, Mireia Nievas was prepared, or some other monitorings that we can use to trigger these observations. And I'll be starting with some of the very interesting results that we have obtained from blazar B laser. This is the archetypal blazar of its type. And since you can see here the Fermi-LAT light curve, and since basically 2020 more or less, you can see that it has undergone a very, very active period with some of the brightest flares, or the brightest flares actually, in the very high energy band ever observed from this source. LST has actually observed these two brightest flares ever from this source in 2021, 2022. That we are about to publish soon. And these are some of the results that we have obtained. We have, of course, characterized the emission during the whole flare, seen a variability of 1 order of magnitude in the very high energy emission, and an emission that was actually even brighter than the Crab Nebula, that is our standard candle. So becoming one of the most of the brightest sources in the whole gamma ray sky, not only extragalactic but also galactic gamma ray sky during this period. And the interesting thing about these flares, as I already advanced before, is the observation of this very fast minute scale variability at very high energies. Here you can see on the left the example for the 2021 flare, in which you can see, for example, this first part of the flare with where the flux tripled its value and then decayed in just an hour, or this example of the 2022 flare with also very fast variability, and this seemingly set of substructures that we have modeled with these rising and decaying exponential light curve models. And these minute scale variability episodes at very high energies are not very often observed, but they hold a lot of information about the emission. First, with them, we can set tight constraints to the size of the emitting regions through causality arguments. So basically estimating the shortest variability time scales that we are able to distinguish in these light curves, we can set tight constraints to the size of the emitting region. And this actually becomes very, very important when interpreting when interpreting the whole the broadband emission of the sources, but also when trying to understand the particle acceleration mechanisms behind these flares. Because actually, the more traditional particle acceleration mechanisms, such as shock acceleration, for instance, have a lot of problems reproducing this kind of features. And so this minute scale variability is often associated with the most extreme particle acceleration mechanisms. And in this case, is magnetic reconnection. So basically, we have magnetic lines of opposite polarity encountering. So they basically annihilate and then reconnect, creating a very fast, a very compact region of extreme acceleration in which this flare is happening. And this is actually something that was supported in the past by particle in cell simulations, hydrodynamical simulations, etc. And solves, as I said, a lot of problems that other acceleration mechanisms fail to explain, such as the need for very, very high Doppler factors that shock acceleration models would need to explain variabilities such like this. And this is actually the scenario that we have used to interpret this 2022 flare from VLAC in this mini jets in a jet model, simplification of this magnetic reconnection scenario, in which these mini jets would be precisely these magnetic reconnection regions, and this extreme variability and very high flux would come from this very extreme acceleration, and these mini jets, these magnetic reconnection regions, being more aligned with line of sight than the actual jet of the source. Of course, this was supported by extensive multi-event campaigns in which actually the IAA has extensively participated. So we coordinated observations, well, of course, from gamma ray energies with Fermi-LAT because it scans the entire sky, but also with Swift in X-rays and UV optical filters, with several other optical telescopes beside the Sierra Nevada Observatory, and also radio and millimeter frequencies. And yeah, this has allowed us to characterize the long-term evolution of the flare. And with this, we have actually managed to model the entire emission of the source. In this case, we have given the very nice evolution of the flare, the brightness of the source during this period, and so on. Instead of just taking one snapshot of the source, we have managed to model the temporal evolution of the flare by identifying periods in which the gamma ray emission was consistent with being relatively constant, and interpret the emission from radio to very high energy gamma rays within a leptonic scenario, in which these small compact magnetic reconnection regions would be driving precisely the variability of the gamma ray band from one snapshot to the other, in consistency with these mini jets in a jet scenario that we proposed for the fast variability. And actually, this paper has been done with well, under the leadership of the IAA, in which both myself and Gabriel participate, showing also the important role of the IAA in the exploitation of the first science of LST-1. Moving to the next result, this would be the observations of the flat spread quasar OP313. This is a blazar located almost at redshift 1, so 0.997. And the interesting thing about this type of blazars, these flat spread quasars, is that so far, before the observations of this particular source, we only knew 9 at very high energy gamma rays. This is first because they are typically found at much larger distances than the VLAC class, but also so they are much more attenuated by the EBL, but also because they have a more complex structure that, as I will mention in just a minute, can lead to internal absorptions of its gamma ray emission, so even complicated even more the detection at very high energies. So this source was actually pretty quiescent before LST-1's observations, but in November 2023, it actually started a very active period. You can see here the Fermi-LAT light curves. So in November, it had this huge flare here that unfortunately with LST we could not follow because this coincided actually with our moon break, so the period during full moon in which our telescopes cannot operate. But fortunately for us, again in December, so just 1 month after, the source went through another active period again. And here we managed to observe it during 15 hours with LST-1. Actually, MAGIC also joined this campaign. And we managed to detect the source for the very first time in the very high energy gamma ray regime. So this became only the 10th known very high energy gamma ray source, well, flat spectrum quasar at very high energies that we detected as a community so far. And not only that, but also the most distant AGN that we have detected so far in very high energies. Still not breaking the Redshift-1 barrier, but we are getting pretty close. And actually, here this is just the press release that the CTAO did as a follow-up of the detection. And yeah, as I said, this is the 10th radiospectral quasar ever detected and the most distant AGN so far. So going to the characteristics, to the results of this source, as I already advanced, of course, we are expecting all the emission very concentrated at low energies because of the very strong attenuation of the EBL, and this is something that you can see here. These are just plots in which I'm showing the number of gamma ray events that we are detecting from the source with respect to the distance to the expected position. So yeah, as you can see, an excess around 0 means that we are actually recording gamma ray events coming from the source. And all of them, almost all of them, we find them below energies of around 250, 300 GeV, meaning that indeed this source is actually very strongly attenuated. And this is also something that we can see from the very steep gamma ray spectrum. So as a distant source, it falls very fast with energy. But this type of sources has, as I mentioned before, an additional problem, that they have very efficient cooling of the relativistic particles, but also very complex morphology, because we have different structures besides the relativistic jet. So we have these molecular clouds, the Broadline region, we have the dusty torus in the infrared, we have the accretion disk, and all these sources can introduce an internal self-absorption of the gamma ray emission. So they can even be more attenuated than just the EBL, than just by the EBL effect. But they are also very ideal for precisely setting constraints to the EBL intensity, because actually measuring the real intensity and the effect of the EBL directly is something very complicated. And in some wavelengths, the EBL is very poorly constrained so far. And the observations of very distant AGNs at very high energies offer the perfect chance of checking the EBL intensity, cross-checking these measurements with different methodologies for studying the EBL, and actually rejecting different EBL models that in some parts of its spectrum, and actually in the part of the spectrum that we can evaluate with distant AGNs at very high energies, are very different one from each other. So this is what we've done with our observations with LST-1, basically defining an exponential attenuation by the EBL, introducing this scaling factor with which we test the intensity of the EBL based on the attenuation of the joint Fermi-LAT plus LST or magic gamma ray spectrum. With this, you can see here that we have set very competitive constraints with respect to other measurements, good in agreement with different approaches, but still highly competitive. And as I just mentioned, in a region of the EBL spectrum that actually shows larger differences between the different modes. So understanding how this EBL attenuates gamma ray radiation is actually very important for us towards the observation of distant sources in the future. Again, to fully understand the emission of blazars at very high energies, we need to coordinate our LST and magic observations with extensive multi-wavelength campaigns to understand what is happening not only at gamma rays, but also at lower energies from radio to optical X-rays, etc. As for BLAC, we coordinated a very extensive observing campaign with different telescopes, again, including Swift, optical telescopes, in which Sierra Nevada, again, from here, was leading the efforts, and also radio and millimeter again. So we managed to model the very high energy, the broadband emission of the source, and compare it actually with the low emission state, so we can try to understand what was driving the flare. Due to this very complicated morphology of this type of sources, these models are often complicated in this case. So we have proposed two alternatives, each of them with some strengths and limitations, of course. But one of them is focused on the reproducing very, very precisely the broadband emission, accounting for the low energy photons that these other regions of the AGN, so the broadband region, dusty torus, introduce, and actually have a very important role in the production of gamma rays through external compton emission. So basically, these external photons from the jet interact with relativistic electrons and produce this gamma ray emission. And a second one in which we focus on reproducing very precisely the temporal correlations between bands, but slightly with a slightly worse fit of the overall emission. In the case of the spectral focus model, we see that it reproduces very well the observed behavior. We see that we typically need here relatively large Lorentz factors, still feasible, but on the high end of what we see that blazars are capable of. But both of them are consistent with a flare being produced by shock acceleration in this case. So again, this paper is under preparation now. It should be actually not yet, but it should be submitted in the next few days. And again, this has been done under the leadership of the IAA that has first led the discovery and the release of this preliminary result, and then all the production of the results and the scientific paper. But actually, more results are coming from this source, because even after the first detection by LST-1 and MAGIC, the source kept flaring and flaring, and even in brighter states. So you can see that with respect to the flare that we managed to detect in December 2023, the source showed even brighter ones with even 2-3 times more flux than the flare that we managed to detect. So even more results, more interesting results on this source are coming. And continuing with the flat spectrum wave quasar topic, just a brief advance of this other flat spectrum wave quasar that we managed to discover, in this case in August this year, this PKS 1725. In this case, the redshift is much lower than OP313. It's only 0.59. But this, again, is a very important addition for understanding more the characteristics of flat spectrum wave quasars at very high energies, in which we see that still its morphology, the location of the gamma ray emitting region, where the gamma ray emission is produced in the jet, is not very well localized yet. So increasing the number of sources that we know of this type is actually very important for us to understand how this subclass of blazars work. And yeah, again, this has been actually the second scientific discovery of the LST-1 after OP313, and the 12th flat spectrum wave quasar detected at very high energies. So there was another one in between that the VERITAS collaboration presented in a couple of conferences between our report on OP313 and the detection of this one, but still we only know 12 of these. And again, this has been done. This detection has been done with the contribution of the IAA, in this case, leading the follow-up multi-wavelength campaign with the telescopes from Sierra Nevada. And yeah, the last, well, more than result synergy with another major facility or set of major facilities in the near future that the LST and the CTAO will have, is the connection between the very high energy gamma ray observations and the high energy polarimetry, and the study that we are actually preparing right now within the collaborations. And I want to start with showing very, very briefly the results of this paper that Ivan and I have published this year within the IXP collaboration for X-ray polarimetry, in which, again, observing VLAC with the IXP satellite for more or less 10 days in November 2023, and again with supported by observations in radio and optical from several telescopes, we managed to observe the most polarized blazar ever in optical wavelengths, reaching a 47.5 polarization, with, however, only a 3 sigma upper limit in the X-ray polarization seen by IXP, and actually a pretty high radio polarization at the level of 10%. And this combination of multi-volume polarimetry basically reveals that the high energy emission of the source, the X-ray emission of the source, is being produced by leptons, so by relativistic electrons. And we can rule out for the X-ray production hadronic emission. And this is actually the first time that we can categorically reject this kind of scenario for a blazar. In this case, up to X-ray emission. So the synergies are very clear with LST and CTAO, because they both have both these instruments have the goal of understanding the nature of high energy emission in astrophysical sources. So following up the IXP campaign, we have coordinated observations both with LST-1 and MAGIC to complement this high energy polarimetry with our observations at very high energies. A follow-up paper using only up to Fermi-LAT data by our colleagues has favored again for the gamma reproduction leptonic emission, but in this case they still leave some room open for leptohadronic options, so mixed emission of both leptons and hadrons. But they predict very different signatures of the very high energy gamma ray spectrum. So here our observations are actually very important to distinguish between these two models. And this is precisely something that we are working on right now within the collaboration with the follow-up campaign that we organized with MAGIC and LST. And yeah, I can advance that basically based on the upper limits that we have managed to set, because the emission of the source was actually very low and we didn't manage to detect it, we can try to set constraints, or even in the best case scenario, trying to rule out the leptohadronic option and confirm, in the case of this blazar, leptonic emission as the main driver of the gamma ray production. And again, this is something that is in progress, and hopefully we can have more detailed results soon, but that again is done under the leadership of the IAA. And now, just to conclude, just a couple of words on the perspectives of extragalactic physics towards the CTAO. So coming back to this figure that I showed at the beginning of the talk, so far we managed to detect at very high energies up to roughly a bit more than 300 sources, if I remember correctly. So thanks to the 10 times better sensitivity that the CTAO will bring, we will basically manage to detect several more sources than we have detected so far. So and of course with much better sensitivity, lower errors, etc. So we'll be able to do much more precise science that we've been doing until now. And this opens the door for many more studies that were not possible with the current generation, such as the objective that I just mentioned in this case, in the previous case, in synergy with AXP, but that is one of the main goals of the CTAO, that is distinguishing between hadronic and leptonic emission in astrophysical sources based on the different signatures of each of these processes in the very high energy spectrum. We can of course make more and more precise EBL studies, thanks thanks to the much higher number of distant sources that we will be able to detect with CTAO, but also thanks to the more precise measurements of the spectra of gamma ray sources. We will of course be able to perform population studies of extra sources and blazars that were not possible until now, because most of the sources that we detected so far were under, as I mentioned before, under the TO program. So these population studies right now would be highly biased towards flaring states. We will aim to see more fast variability events that can be associated with the most extreme particle acceleration processes in the universe. So we will be able to study more in detail these particle acceleration processes, and even more detailed studies of the ultra-high energy cosmic ray origin based on extragalactic cosmic ray emission. And yeah, as final remarks, I just want to remind that CTAO will basically revolutionize the gamma ray astronomy field. We are already obtaining very, very interesting results with LST-1, and actually 3 more LSTs will come during next year. So very, very soon we will have the most sensitive Cherenkov telescope in the world. And yeah, we've already managed to detect a lot of sources and to run very, very successful target of opportunity campaigns in which we have seen some of the most extreme flares and variability events in the gamma ray band ever. And we are actually already discovering new sources. So this is the proof that the LSTs are very well suited to break this barrier of redshift 1 in the very high energy gamma ray universe and expand our knowledge of the most energetic part of our universe. And of course, very interesting synergies are opening with other major facilities like IXP, or for instance the future COSI NASA mission in a couple of years. And yeah, I just want to remind that the IAA is actually leading a lot of the efforts on exploiting the first scientific data of the LST-1, and they are producing a lot of interesting results. And also a message to all of you, CTAO will be soon an open observatory, so also think what CTAO can do for your science. And that's it from my side, and yeah, let me know if there are any questions.
Thank you very much, Jorge. Thank you for the medals that you have given to us regarding leadership on AGM research with LST. Okay, are there any questions?
Oh, thank you very much for organizing. Oh, it was very light for tonight. Well, I have a couple of questions. The first is you mentioned 2 bursts. The question applies for both actually. Then that you have made a multi-wavelength campaign after radio, optical, multi-wavelength basically. I am interested to know if you have looked for it or not, any time delay between the different wavelengths. First, there is, if there is, why? If there is not, why? Because we also see bursting young stars, and we do see delay like echo or whatever. So can you say a few more words on that?
Yeah. So this is actually something that we often do for our sources, basically because it has a lot of implications when it comes to explain the whole emission. Because when you see delays, basically what you're seeing is that some of the emission is coming from different parts of the jet. So you need to understand how the jet is, how the morphology of the jet is to see, let's say, how many emitting regions do you need to use for modeling the whole emission and these kind of things. For the case of VLAC, for instance, well, I can speak for the 2022 flare. We actually didn't see any time delay. Apparently, all the emission seems to be coming pretty more or less at the same time, except maybe for the radio that shows much lower variability. But this is actually something that we see pretty often in blazars, because typically the gamma ray production is the gamma ray emission is produced in regions very close to the central black hole, so very inner regions of the jet. But those regions are also highly opaque to radio wavelengths. So there's a lot of internal absorption of radio emission, and we typically assume that radio comes from an outer part of the jet, because we, in many cases, in longer campaigns, of course, because this is just a 2.5-month flare, in long campaigns lasting a few years, you can see delay of the radio emission by several hundred days.
Would you expect also implication of the optical depth or the extinction toward a different wavelength? Because if everything comes from the same thing, I mean, I would expect that optical maybe would be more obscure than radio, for example, but now you say that radio is self-absorbed. Can you?
Yeah, that can happen, but mostly for radio. That's the most important internal absorption or extinction that we have in the jet. typically optical tends to correlate pretty well with gamma rays, with Fermi. So we usually see that they come from, if not the same region, regions that are very, very, very close.
Yes, one question, please.
Thanks, Jorge, for the presentation. I have a small curiosity about the fast variability of VLAC. So you said that the interpretation is this magnetic reconnection of these mini jets in the jet, and I was naively wondering whether there could be other interpretations, like I don't know, a cloud passing the line of sight of the jet, or something like, or would you expect such a fast variability in those?
Yeah, actually, that can also happen. I remember a paper from the MAGIC collaboration from a few years ago on another flare of VLAC. I think it was, well, I don't remember the year, but before 2019 for sure, because I think the paper is from 2020, more or less, in which they actually explained a similar event, not so bright, but similar event with fast variability and so on, with, I believe it was a star crossing the jet. I think in this case it was a star crossing the jet, but in this case we opted for the magnetic reconnection scenario because basically we see a flare developing over several months and also with several ups and downs. So it seemed more realistic to have like a magnetic reconnection region that is appearing over some time than having like several stars closing so fast in such a short period of time and so on. But it is possible for sure, yeah.
Thanks.
Paula?
And I was asking if you know something, what can we learn from this plot about the acceleration mechanism? For example, I don't know, maybe you can somehow constrain the size of the plasma or like.
Well, from this plot in particular, what I mentioned before about constraining the size of the emitting region based on the shortest variability time scale that we are able to resolve. In this case, we resolve like 8-minute variability. And from this, you can already see that the acceleration region has to be very, very, very compact. And I'm not sure if shock acceleration can reach such compact sizes, but it's not directly from this plot, but just from the fact that this kind of fast variability to be explained with shocks usually needs very, very high Lorentz factors. And these Lorentz factors are not often, is what we call the Doppler crisis, are not often supported by radio observations in which we can measure the velocity of the material propagating through the jet or things like this. So magnetic reconnection actually solves this problem because you can have these magnetic reconnection regions, these mini jets, more closely aligned with the line of sight than the actual jet. And this is what produces an additional relativistic boosting without the need of huge Doppler factors.
Question by Jacob.
Super nice. Coming back to the VLAC timings, rise and decay, if you go back to the slide, it looks like there are different time scales of the rise and the decay. And I wonder if we manage to have a statistics that is sufficient to find the trend, because if the two are symmetric, the easiest explanation is that it's the causality time. But if you have asymmetries, then one is connected more to the microphysics, radiation time, cooling, and so on. And so it would be very nice because the one that is determining your dimension is actually the fastest of these, which may look like the first rise, for instance, this one. So it's very interesting to have these different trends, and it would be very nice to try.
Yeah, I agree. I mean, this kind of events actually can have a lot of implications in that in the cooling and acceleration and cooling conclusions that we can obtain from them. Of course, here, since we have, it seems that we have several substructures, it becomes a bit more complex. Also, because when you model with several exponentials, then it becomes a bit more complicated to see if all of them are symmetric or asymmetric or so on. But this is something that it could be actually easily tested with the 2021 flare, because here it's clear that there's a rise and decay, and well, here there's a bit more scatter, but at least with this first peak, it can clearly be evaluated. But of course, as soon as we have more sensitivity, this will be much easier. We will have lower error bars. We can perhaps even push to shorter readings or shorter time scales. So yeah.
Very interesting. Just a comment on BLAC. There are lots of data from Siena optical, but tons of them that for some reason didn't go through. Maybe we can involve them. While for P313 there is some basics time series study that is being done by a student in Siena who's graduating next week, and then maybe we can try to involve him because he's doing a nice work.
Yeah, we can talk about it.
Great. I just have one short question about the study for the emission processes. Electronic
With
versus
HPA.
hadronic here in BLAC actually.
Yeah.
When you were talking about the flare, the fast flares, you were also considering. You said that you modeled with electronic models, the broadband LSTs. But did you consider also the option of hadronic models?
Well, in this case, we went for leptonic, basically also based on the IXP results. It's true that there was not a simultaneous IXP campaign with this flare, but unfortunately for us, IXP observed, I think it was 2 days after we stopped observing this flare. So, and it was not as clear as the paper that we have done, but they also favored leptonic emission.
Okay.
And based on that campaign and also our paper, even if it's from posterior observation, we opted for leptonic, and also because BLAC is not really a strong candidate for neutrino emission, so it was not strongly justified to go for a hadronic option.
But then on the other study that you showed, actually you are ruling out hadronic emission because of the spectrum, isn't it?
We are trying to rule out hadronic emission, exactly.
Because of the spectrum.
Yes, because of the upper limits. Yeah, this is still not definitive, of course. These models are highly degenerated. You have a lot of parameters to play with, so you can find several solutions that fit your data. So what we are trying to do basically is do like a complete scan of the parameters describing the jet and the emission, and see if after doing this scan we can completely rule out the leptohadronic emission, or if we cannot completely rule out, at least we for sure will be able to constrain it much farther than the previous study that has done by our colleagues. And also based on this, in case we can rule out this hadronic option, we are trying to evaluate if there was a very, very subdominant hadronic component below the LST and magic upper limits, what would we need in terms of exposure, sensitivity, etc. to detect.
Okay. Super last.
Yes, just to add some grain of pepper in the. It's true that in the assumption that the magnetic field in the emitted region, the low X-ray polarization found by Higgs for BLAC tells you that it's leptonic and not hadronic. But Fabrizio Tavecchi and Filippo Bollis are working on some hypotheses with the structured magnetic field where the hadronic emission may be compatible with the observation. So this is ruled out under the assumption that the emitting zone is super strong.
Yeah, that's true. And I saw actually the paper that they published. I think it was
it's not a criticism, it's just the reality.
No, of course. I mean, my feeling, without being a huge expert on theoretical models, my feeling was that that model actually, the one that they proposed, had some very extreme parameters, for example, the strength of the magnetic field and so on, but still some solutions are possible, and they are showing
just to tell that
exactly.
We never say the end.
No, of course. And we know in the end that all the models that we are doing here are oversimplifications of the real jet, because we are just using 1 zones, 2 zones that are not, what most likely we are seeing.
For instance, some of the chromatic effects that he was mentioning in the question are also in the gamma bands due to the density that sometimes for some frequencies may make the region self-opaque, and as you said, high Doppler factors mitigates this effect.
Yeah.
So it's really a complex.
Yeah.
All right. So I think it's time to go lunch for lots of us. So thank you very much, Jorge.
Thank you.
And